All right, hello everybody. So today, let me see if I can adjust this. So today I'm hoping to do bunch of problems associated with chapter 3 and primarily chapter 4, just so we are up to speed. I got couple questions and couple requests on how to do certain problems for chapter 4. So we're going to be looking at that. Let me see if there's anybody else asking anything. Ta, 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 ta. No, I got mostly questions about chapter 4. So I'm gonna do that, and then if we have more time, I will go back to chapter 3 and we can talk binomial. That's the plan for today. So we're going to be dealing mostly with chapter 4. Again, since I don't have a very large response on what might be needed, I'm doing what I think would be needed and what some of you have requested. So, in that respect, bear with me. All right. So let's talk about the possible questions when it comes to chapter 3 and 4. In today's discussion, we're going to be looking at things that are associated with the normal distribution. So for chapter 3, what we had was the introduction of and the use of the z-score. And what the z-score does is it takes some normal distribution with a mean of mu and some sigma. It takes a mean, which says, hey, find the probability that x is greater than some number. Let's call it a. And so if a is bigger than mu, we say, hey, there's a. And what we're looking for, this area. That's what this means. The problem with that we found is that to do this using this equation and this kind of setup was that we don't have the necessary math ability to do this. What we do have is we know how to deal with a standard normal. So this is some normal distribution, and this is a standard normal distribution. And so we can go from here to here using the z-score, and our a becomes some z, and we still want this. And then we take our z-score table and we find both probabilities and we decide which one we want to put as an answer. So that was the basic idea in chapter 3 when it comes to z-scores. And we're going to do a couple of problems with that. In chapter 4, in chapter 4 we expanded on this idea. So in chapter 4 we expanded on it and we got the following. Because we are no longer talking about a single data value, we're talking about an average of a sample or a mean of a sample. So we expanded the z-score to account for the fact that the more an average is away from the mean, right, the lower probability that has, right? Finding one super tall person is tricky but not impossible. Finding 100 people who have an average of a super tall person, nearly impossible. So that was the idea. And so how we dealt with it? Well, we had some normal distribution. Instead of x, we had x bar, and again some value. We converted to a z, and from there we moved on. So that was first part. Second part is we build confidence intervals, and confidence intervals for means. So for mean, population mean, looked like this. Okay, we had x bar given to us in the question, but we needed to find the margin of error. So the margin of error had the following formula. Easy enough. We got z alpha over 2 from a confidence level. So sometimes we got confidence level stated as a percentage. Sometimes we got 1 minus alpha. So whichever way it was denoted, we had a confidence level, and from confidence level we could find z alpha over 2. And we have this. But then we realized that we can have a small sample where we don't have the population standard deviation, and we got this. And then in some problems we also going to find that although we want to use z alpha over 2, we don't have population standard deviation, and we get this. And oh my god, 3 formulas to do the exact same thing. So how do we decide which formula we use? Well, we're going to use a priority list. If we know sigma, then we use that, no questions asked. If no sigma, then we have 2 questions for n greater than 30 and for n less equal to 30. If we have a large sample, and we can say that S it's about sigma. If you have a large sample, the standard deviation of that sample should be close-ish, somewhat about approximate population standard, which means that we can still use z alpha over 2. But if we have a small sample and no sigma, we're going straight to here. So that's the basic notion. If we have sigma, this. If we don't have sigma, we pick whichever one we have based on the sample size. Alright, so we had that. What else did we have? We had confidence intervals for P. So still in chapter 4, we had confidence intervals for population proportion P. and that was p hat minus e smaller than p hat plus e. Okay, what was e? Well, e was z alpha over 2 p hat q hat divided by n. And that was it. There was not much more to it. And if you look the back of your script, let me see if I can pull up my. Yep. If you pull up the back of your script, you can find all those formulas there as well if you don't want to look through the chapters. All right, so that was another thing we did. We looked at confidence intervals. What else? Sample size. Sample size was, well, it was either what was it? It was either for how do I right let's do it this way. It was either this, the critical value times a standard deviation divided by e squared, and again, if you don't have sigma, you had ns, but you used an s because you use whatever you can. You denote which one you use, but you use whatever one you can, and then you can fix it afterwards. Or in case of proportions, you had the critical value divided by the margin of error squared times PQ. Or in this case, you could have a P hat Q hat. So you did a small pre-sample and you got some values. Or you have a P and Q historical data, and again this. Or you have neither and you have no way to estimate it. And in this case, we're doing the worst case scenario where we supplement halves for each, and that gives us this variation. Right, so for sample size, if we're talking about means and averages and standard deviations, we have this one, critical value times the standard deviation divided by margin of error squared. Or if we're talking about proportions, we have critical value divided by margin of error squared times some indication on how P and Q are going to behave, either from a small pre-sample, some historical data, or worst case scenario to do this. And the last set of problems that we're going to take a look at today is again, that's chapter 4 problems, and that's approximating binomial distributions using normal distribution. And in this case, what we're going to have is we're going to get some question say what's probability. That. What's the probability that the sample average is going to be below 50%? Well, this average came from some population. So what we're going to need to get is the sample size and the population average. In normal case, we would pull up our trustworthy binomial distribution table and try to find all of it in here. And again, that is very doable, and we could calculate all the little aspects of it in here. We could do it using the binomial formula for each value and the binomial formula for was that. We could have done that. We could have used the table and dealt with specific probabilities. But if we have something like this, well, we could be looking at it was what is p hat. P hat is really x divided by n. Well, if p hat is x divided by n, what are we really looking at? Well, what we're looking at is a hidden x, which is p hat times n. So if I multiply both of those sides by n, what I'm really looking at is that. And that starts looking like something we already seen before, right? So this is interesting. Well, what is n and p have to do it? Well, we can find the mean as n times p, and we can find the standard deviation as n times p times q. And we could attempt to solve it. And again, that is reasonably doable because in this case the z-score right, the z-score, we could fill in the blanks and we could do this. Now this is a lot of work. What we could do instead of this is we could look at what would happen if we just used that. If we use that, what we skip over is all this, and we look at straight to the problem. We have some p hat, right? We have some n. We have p, which means we have q, and the whole thing is solved. One of the homework problems I assigned to some of my students looked like that. And we're going to again do some problems that look like this. So instead of dabbling with this and trying to figure out what's the mean of a binomial distribution, or what's the standard deviation is of a binomial distribution, sorry, that should be a square root, right? Instead of looking at this and solving this, right, we get this. Now, is this solution wrong? It is not wrong. Why? Because if we expand this, what we get is, right, I'm just plugging in our very basic things. So what is that? Well, this is can we take maybe something out of here? Well, and what is this little section? Well, this is, so n equals to, and since n is always positive, that's not an issue. So if we do this, that's just square root of n. So this becomes p hat, sorry, this should be square, p hat minus p divided by pq square root times square root of n. That gets us back here. So even if you do all these steps, you still arrive at this, which makes it just much easier to use that. Now there's some requirement for approximating binomial distribution in normal distributions, but those we're gonna talk about again at some other time. And this is the last type of problem we're gonna do today. So either pure z-scores or sampling distribution with some averages, or confidence interval for mu, or confidence intervals for p, or sample sizes, or attempt to approximate binomial distributions using this. Right. So this is the basics for today. Let me see. Any last minute questions? No. And no. Alright, so I need to figure out how to post documents online so everybody can get access to it beyond my class. When I figure that one out, I'll post the document I'm using right now in the description. But for now, just bear with me. So here's a set of problems. It's a PDF which has a long list of shear numbers. And this is the first type of problem. The problems here are have to do with what I would consider chapter 3, and they have a very simple, let's solve it using this. So what we have is some n, some sigma, some mu, and some x, and what we need to get from here, we need to get to p, to some probability. The problem is we don't go straight through probability, we go through something called the z-score, from x to z-score to probability. And that's all there is. So let's solve it. All those problems have the following feature. They're randomly generated, so all the calculations for the z-scores and the probabilities that you see over here are made by a computer, which means that when you do things with a table and on a handheld calculator, those numbers might look slightly different. If they look slightly different, I won't worry about it. If they look radically different, then either I made a mistake programming the answers in, or there was an error in your calculation. I'm betting it's the error in your calculation, but that's not always true. So what you see in the blue columns are answers generated by the Excel program. So there's some randomly generated data in the gray area and some answers based on that randomly generated area in the blue. So that's the basic idea. And then again, there's about 30 some problems for each type. I'm gonna do the top 5 for each, and hopefully that will give us enough variation on data that if you ever get struck with a problem like this, you shouldn't have an issue. That being said, how many problems do you need to do to be good at it? I say you need to do between 5 and 10 minimum. You need to get to a point where you can solve one of those lines in under 5 minutes without any issues. This will give you ample strength to approach the exam. I would, for people that are ambitious, I would aim for about 3 minutes per line. That's about the right speed. So let's start cracking. We want to put a timer here. Do I want to embarrass myself? No, I don't want to embarrass myself. I'm gonna say the YouTube video is just slow. All right, so first problem. Actually, let's go back. The first problem is, because we are talking about a single data value, do I really need to know n? No, I don't. It's an extra piece of information. Some problems have extra pieces of information we don't care about. We need sigma, we need mean, and we need an x to calculate z-score, because once we have the z-score and a picture, we are quite comfortable getting the probability. Now, on the exams, the problems won't look like this. The problems will actually look like this. You will actually have a description, and you're going to have to figure out how to deal with the description. Here, I'm just looking at numbers. If you need problems with descriptions, just let me know, and I'll do my best to type some up or make some up, and then we can take it from there. All right, so this is this. I'm gonna put this here. All right. So first problem, 108 students have bills with a population average. Okay, so 693.8 with a standard deviation of 26.2, and what we're looking is for probability between 722.9 smaller than x smaller than 736.5. This in a problem would be, what is the probability of finding whatever we're looking for between 722.9 and 736.5. That's this. Alright, well, this gives us two x's. There's an x1 here and an x2 here, right? Because those are the border crossings. Because again, what we are going to be doing is we're going to take some normal distribution with a mean, in our case 693.8, and a standard deviation of 26.2. We're going to find those two values. Where are they? Well, there's one here at 722.9 and one here at 736.5. 36.5, and we're asking about this probability. Well, we cannot really do that, but if we z-score this distribution into standard normal, the middle is 0. This will become some z-scores, call it z-score 1. This will become some z-score 2 with a probability in between, right? That was our x1, x2. This and this, right? Because it's a standard normal, we can find using our z-score table. So let's do this. So we need to find our z-scores. Our z-scores are calculated by x minus mu divided by sigma, which means we have z-score number 1, and that's x1, which is 722.9 minus 693.8 divided by 26.2. Today I'm using a cheapo calculator, and it's 722.9 minus 693.8 divided by 26.2, and I got 1.11. Why am I only using 2 decimal places? Because my table only gives me the z-score up to 2 decimal places. And then we have our z2, which is 736.5 minus 693.8 divided by 26.2. So 736.5 minus 693.8 divided by 26.2. And I got 1.6, and I am going to round it to 3. And again, if you look right here at the 2 z-scores at the top line, I got the same thing. All right, well, picture 0 in the middle, artistic freedom, say 1.11 is here, 1.63 is here, and we're looking for the area in between. So we're looking for this area. Okay. We look up this probability and this probability. So 1.11, according to my table, 1.11 is 0.86650. 1.11, we got this. And 1.63 gives me 1.6 and 3. I get 0.94845. That's according to this table. If I look at another, let's just give a different result. 1.1, 1.63. Yeah. I have a different set of tables here, and what I get according to this table is 9484. Right. So this table, because it has 4 decimal places, it gives us. And again, which one is correct? Well, whatever the table that you're using is. My answer key right here says 0.9484, so it's leaning towards this. What this table gives me gives me one more decimal place. Again, because we are rounding, and because the tables are the way they are, you have to make a decision about it. Either one of those wrong? No. This one is a little bit more precise than this one, but doesn't mean it's more correct. It just has more decimal places. This is the z-score table I grabbed, and since I'm swarming in z-score tables, not all of them are exactly the same because the number of decimal places. Right? And again, I provided an acceptable answer here. If yours is a little different, for example, you round this to 8485, that's okay. Again, I'm going to use the numbers I have on my table, and let's see what do I get. So I'm going to take the big probability minus the small probability, so 0.94845 minus 0.86650, and I get what? I get this, that this area is 0.08195. So that's 8.195%. And again, if I round this, I'm going to get 8.20%. The answer, according to the problem that I posted, is 8.19. And that has to do with this little thing. Again, this is little off from here, but doesn't mean that this is not a correct answer. I'm okay with answers being different than my answer key. If I get an answer that looks a little different than mine, but everything else looks correct, then that's just a little error of rounding somewhere, and I let those go. If this answer is very different from what I would be getting according to this, then I'm gonna go step by step, be like, hey, wrote everything out, check. Okay, there's some formula, check. Points for here. Z-score calculator, check. Picture, check. One probability, two probability, and I'm gonna double check them with my table just in case they look off, and then final answer, check. And this is how those things get graded. There's a point here, point, maybe point for both, maybe point for each, and then a point for the answer. Partial credit. If you just give me this and that looks off from my answer, well, too bad. But if you give me all that and this is slightly off of my answer, you're still okay. So this is how you do the first problem. Alright, next one. Again, we don't care about n, so I'm not worried about it. So let's see what we have. We have a mean of 404.6, sigma of 2.21.4, and we're looking for probability that 356 is smaller than x, smaller than 79.8. Okay, well, that's our x1, that's our x2, so our z1 equals to 356 minus 404.6 divided by 21.4, and we should get negative 2.27 out of this, and our z-score 2 is 379.8 minus 404.6 divided by 21.4, and we should get negative 1.16. So negative 1.16, say here, negative 2 0.27 right here, and we're looking for the area in between. Well, let's see what is this probability and what is this probability. Look at this table with only 4 decimal places. Negative 1.16. I'm getting 0.1230. Maybe I should do this right here. Right, this is the 6th column, 1.16. Stop moving. And again, I'm happily it matches what's written out here. Alright, let's go back to white. So this was this. Now negative 2.27 I got 0.0116. And so what is this area? Well, this area is the bigger one minus the smaller. So this probability equals 2.1230 minus 0.0116, and the probability and again, very luckily, it matches. Okay, let's do one more. Mu equals to 4949. We have an S 29.1. We have a large sample, and then we have a probability that X is smaller than 560.4. Okay, because N is greater than 30. S could be treated like a sigma. In reality, we wouldn't like to do this, but in reality, we don't usually have sigma. So if somebody went out of their way to find their sample, to calculate the probability, this is what we have. So we don't have any better piece of information, so we're going to use it. Again, our z-score is still going to be x minus mu divided. It's still going to be x minus mu divided by sigma. Just instead of sigma, we're going to substitute this, as this is the only thing we have available. Now again, we would prefer to have sigma, but this is what we have. This is what we're going to deal with. Now you're more than welcome to write that this problem is unsolvable because it doesn't fit a formula, but this is a 300 level class. I expect some ingenuity on solving it. So this. Alright, so the z-score equals 560.4 minus 494.9 divided by 29.1. a question was posed: how do I know that I'm just talking about x equals 560.4 and not smaller or larger? And again, that brings us back to this initial conversation where those are, oh, sorry, these are the axes that border the area that we are looking for. We don't necessarily care about axes that are in between or outside. These are the ones that slice this area apart, and z-scores are border scores. Those are scores that separate areas in case of confidence intervals between likely and unlikely when it comes to hypothesis rejection and not rejection, and so on and so forth. So what we are looking for is this line, right? It's this question of how far can I draw till I get off the paper. Do I really care about this? No, I care about the last piece or the last pixel, the last space on the paper I can draw on before I hit the desk. And this is that edge or that line that we are trying to figure out. That's why we are just looking at the border x and not everything else. And again, if we calculate the z-score, that comes out to be 2.25. Okay, well, and we're looking for x's that are smaller. Artistic freedom says 2.25 is here, and we're looking for less. It's going to be a big area. All right. Well, so how big is that? We look at our table, 2.25, and I get that this area is 0.9878. Ta-da. Why this? Well, because the z-score gives the probability to the area to the left of the z-score, right? So z-scores, the probability to the left of this is what's given up on all those tables we have access to. All right, well, that was easy. All right, let's look at the next section. Maybe I should do this. For those of you who don't have access to my class, and I doubt we have a lot of those listeners, but just in case you want more of those problems, sorry. What do we do? Here's a section. Just take a screenshot and work from there. Right, let's get to the next set. And again, for people that are interested in the whole thing, here it is. Screenshot or pause. All right, so now things change. So let's look at problem number one. Now we're talking about the probability that is asking about this. It's asking about what's the probability that the sample average is going to be between 74.3 and 81.9. Well, This is great, but now we have an x bar. We know that we can get from an x bar to a probability through a z-score. But this z-score is starting to look different. A little different. It's x bar minus mu divided by sigma times square root of n. Again, times square root of n is the same thing as that. Those two things are equal, because dividing by a fraction means to multiply by its inverse. So these two things are equal. This is easier to plug in the calculator, but this formula shows up more in my notes. Yeah, so this is it. Alright, so let's see what we have. Well, now we need n, so n equals to 19. Sigma equals to 30.8 and mu equals to 78.0. Well, we have two z-scores, so z-score 1 is 743 minus 78.0. Again, x bar minus mu divided by sigma 30.8 times square root of n, which is 19. So that's 74.3 minus 78 divided by 30.8 times 19. And I come out with z1 equal to negative 0.52. Look at that. It matches. Z2 will be 81.9 minus 78.0 divided by 30.8 times square root of 19. And our Z2 comes out to be 0.55. Okay. Oh, negative 0.52 and a positive 0.55, and the area we want in between. I see another question here, and the question is, can we ask for the area on the outside? Yeah, you could have this set up in such a way that I'm asking you what's the probability of finding this outside stuff, and that's again doable by itself. Alright, so let's see, this whole area, negative 0.52 is 0.3015, and again you have that answer in this column, and then the area for all of this, I mean all the way down, 0.55 is 0.7088, and again you can see that in this column, and if you take one away from the other, you're supposed to get that this is 0.4073. which means that the answer, final answer is 40.73%. And again, I would prefer it to be written in this way. This equals to 40.70%. And then boxing is nice because that's easier to grade. So this is what this looks like. It's not much more difficult than this, with one exception. You have to, multiply by a square root. Alright, next one. N equals to 27. Sigma equals to 259. Mu equals 715.8. And what we're looking for is probability that X bar is smaller than 623.1. The other thing is, in most part, the problems which you can get are designed or calculated, back calculators to have nice numbers. So for the most part, I wouldn't expect a z-score to be, for example, negative 17 or plus 90. Like, you shouldn't be getting numbers like this. They might be low, big every now and then, but very rarely. So, all right. So z-score, x bar minus mu divided by sigma times square root of n. So 623.1 minus 715.8 divided by 259 times a square root of 27. And so our z-score comes out to be, I know I have the answers there, but I want to make sure that I get it right, or that I did it right the first time around. 259 times square root of 27. Negative 1.8556. Okay. All right. So we have that. Now my normal distributions look horrible today, and that's okay. Negative 1.86, and we're looking for this. And negative 1.86, and that comes out to be 0.0314. So the probability here is 3.14%. And again, the probability you can find it in this column, and final answer in this column. Check. One more? Let's do one more. Maybe we can fit it here. N equals to 9. Sigma equals to 1475.7. Again, we don't care how big or small the numbers are. We can just do it. Oh, that's a weird situation where the standard deviation is huge by comparison to the mean, but that's what it is. And we were looking for x bar smaller than 1453.6. So again, the z-score is 1453.6 minus 892.8 divided by 1475.7 times square root of 9, which is a 3, and we get the z-score to be 1.14. Zero in the middle, 1.14 here, and we're looking for the area smaller, so 114. 114 is 8729. And so the probability is 87.29%. How cool is that? And that ends the second set. Alright, I'm going to take a quick break, about 3 to 5 minutes. I'm going to get some more water and then we can keep on rocking. All right, I think hopefully I'm not the only one back. Wow, 3 concurrent viewers. This is wow. This feels um, this feels fancy. Anyways, all right. So let's. What did we do? We did number 3. So we did the last set. Again, if you want to see more, there it is, and we're moving on. All right, so here we have a set for testing confidence intervals for P. So let's do, say, the top 3. Did I make a mistake? I'll get back to it. All right. So hang on, guys, just double checking something. All right. Sorry about that. Apparently, I added the wrong page in the middle of it. Let's not worry about it. All right. So that's not what I was going to do. Confidence intervals for P. Right. Yep, that's the one. All right, confidence intervals for P. Sorry, the technical difficulties. Apparently, I'm not as savvy as I thought I was. All right, so confidence interval for population proportion. The basic idea was, again, we took a sample, and somewhere around this sample is the population proportion. And by is, I mean we are some confidence level sure it's there. How sure are we? Well, depending. In our case, the confidence level is right here in the middle. We're 90%, 95%, 99% sure, and that number will be generated for you. In odd cases, that number will be different than 90, 95, and 99% because I want to challenge you or because I want to see if you can find critical values. But that's the basic idea. And then we know that E is Z alpha over 2 PQ divided by N. Now, again, do we have P and Q? Or maybe we have P hat, Q hat, or maybe we have nothing. Right? And again, if you take a look at some of the options, in all our cases we have P hat. Now, why we have P hat in this case? Because we are trying to find P and Q, so that aspect has to be P hat here. And we cannot have a margin of error not having anything, right? Because again, our margin of error is based on our sample. When you start having this kind of conversation here, what you are thinking is about the sample size when it comes to population proportion, which is N equals Z alpha over 2 E squared times PQ times P hat Q hat times that. So when you're starting to have this kind of conversation, are we talking P hats P and Q, P hat, Q hat, or half? We're talking about sample size. When we're talking about finding or estimating a P, right, of population proportion, we only have P hat, Q hat to deal with because we took a sample. We only took, a small sample, and based on this sample, based on how big it is and how confident we want to be, we estimate how much error we have in our approximation of the range in which we're going to find P. Right? Those two will get mixed up a lot, or statistically or historically they have been mixed a lot. Again, when you start wondering which formula goes for where, and you don't seem to be able to find it on the exam, or you don't have it in your cheat sheet, or you're confused or whatever, remember this: when we actually take a sample, we do have P hat, Q hat, we have N, and we're estimating where P is going to end up. So this is the only option. On the other hand, when we are trying to figure out how big of a sample we can take, well, we have three choices. We have some sample that we took to estimate what the proportion is. We have some historical data, or we have the worst case scenario. Right? But this is only when we're trying to figure out how big of a sample we take, rather than we took a sample already. If we took a sample already, we have P hat, Q hat. We know how many successes and how many failures we had. Right? So this is the big difference. Right? So again, our confidence interval for P is right. So that's what we're looking for. And again, RE is Z alpha over 2 PQ divided by N, and which PQ? Well, P hat, Q hat. we took a sample. This is based all on our sample. We took a little sample and we're going to say something big. So we have a statistic and we're trying to talk about a parameter. All right, so problem number 1. We have n equals to 95, x equal to 85. We have a p hat. We have a confidence level, which is denoted by 1 minus alpha at 90%. Any questions? No, so far so good. All right, so first things first. Why the hell do we need all of this? We don't. We only need half. We need n. We need n. We definitely need that. And then, depending on how the question was phrased, we either get x or we get p hat. Why? Because p hat, by definition, is x divided by n. So if we have x and n, we have p hat. If we have p hat and n, we can calculate x, although we don't need an x in here. We need a p hat. So if you have p hat and n, you're peach. If you have x and n, then you need to calculate p hat, right? So again, the problems I have here have a little bit more information than you need to solve the problem. And again, you have to figure out why you need something. The easiest way, write the formula down and see what you need. P hat, Q hat, n, and z alpha over 2. All right, we have p hat. What is Q hat? Well, Q hat is a complement of p hat. So that would be that. And that would be 5, 0, 1, 0. And so we have Q hat. What else do we need? Z alpha over 2. Well, either you remember or you can look it up in a table. Right? There's several ways you can do it. I remember that this is 1.645. And again, there's the answer just in case you need it in this column. So I try to calculate my E, and that's 1.645 square root of 895 times 0.105 divided by 95. Alright, so our E comes out to be 0.895 times 0.105 divided by 95. Excellent. Square root of the answer times 1.645. And I get 0.051738. Well, so let's take a look at p hat 0.895 minus 0.0517, and the other one is 0.895 plus 0.0517. So this comes out to be 0.9467, and the other one comes out to be 0.84333. So our confidence interval is and the answer is we are 90% sure that the population parameter is going to be between 84.33% and 94.67%. Let's look at the next one. N equals 144, x equal to 37, which should gives us a p hat of 0.257, and we have a 1 minus alpha at 95%. So q hat equals to 1 minus p hat, which equals to 3, 4, 7. So q hat is this much. Alright, so our E equals to z alpha over 2 p hat q hat divided by n. How big is z alpha over 2? For 95%, z alpha over 2 is 1.96. So this is 1.96 times 0.257 times 0.743 divided by 144 and then square root. And if you do the calculation, this should come out to be about 7%. So 0.0714. How would I plug this in the calculator? I would calculate the middle first, then take a square root of it, and then multiply this. Let's see if I can do a demonstration. Where are my calculators? So in our case, 0.257 times 0.743 divided by 144 square root of the answer times 1.96. And there's our answer. And then instead of 3.7, I round to 4. And then what's our interval? Well, it's p hat minus e smaller than p hat plus e. So that's 0.257 minus 0.714 smaller than p smaller than 0.257 plus 0. There's a 0.714, which comes out to be 0.1856 smaller than p smaller than 0.3284. And we're done. Next one. N equals 594, x equals 264, p hat equals 2. Well, let's calculate p hat just to double check if I have the right thing. 264 divided by 594, right? Because p hat is x divided by n. In our case, that comes out to be 0.444 and 4 repeating. So q hat equals 1 minus p hat, which equals 2. 1 minus this, 1 minus 0.444, which comes out to be 655. 655. So our margin of error is z alpha over 2 p hat q hat divided by n. How big is z alpha over 2? Well, if alpha is 1 minus alpha, the critical level is, the confidence level is 0.99. We know that z alpha over 2 is 2.575. So this equals to 2575 times 0.444 times 0.556 divided by 594. And that gives us an E of 0.0525. 4 times 0.556 divided by 594, square root of the answer, times 2.575. 0.444 times 0.556 divided by 594. Square root of the answer times 2.575. Okay. It comes out to 0.05249, so 5. And then again, it's p hat minus e smaller than p hat plus e. So that's 0.444 minus 0.0525 smaller than p smaller 0.444 plus 0.0525, and that should come out to be 0.3915 smaller than p smaller than 0.4965. We don't know what the population proportion is, but we are 99% sure it's somewhere between 39.15 and 49.65%. And that closes confidence intervals for P. Good. Moving on. Let's see what we have here more. Awesome. Let's do this. Whoa. Come back. So what we have here is a list of problems for confidence intervals for population mean. There's one error in this, is that instead of alpha, this should be 1 minus alpha. Confidence level is 1 minus alpha. So confidence level is 1 minus alpha, not alpha. Alpha is significance level. So there's a error here, so just bear with me. But here's the list. Screenshot, pause, whatever you do, and then we're gonna go back to the top 3, and let's try to solve them. Top 3. Let's do top 3. All right. So again, confidence intervals for mean are x bar minus e smaller than mu smaller than x bar plus e. So let's see. For the first one, we have n equals to 40, s equal to 5.1, x bar equal to 52.5, and 1 minus alpha equal to 0.9. Again, that was there's a typo there. Instead of alpha, it should be 1 minus alpha. I'm sorry. All right. So, what do we need? X bar we need to calculate E. And here comes the tricky part. We don't have sigma. If we remember our conversation about it. Hey, where's that piece of paper? If you remember the conversation about it, we had this list. Do we have sigma? Well, we don't. We have S, so we have no sigma. Sample bigger than 30, smaller than 30. Our sample is 40, which is bigger than 30, which means that we're using this, right? Because n is greater than 30, we're going to use this approximation. And so this is z alpha over 2 s divided by square root of n. Well, what is z alpha over 2? Well, z alpha over 2 for 0.9, right? So 1 minus alpha being 90%, z alpha over 2 is 1.645. So our E is 1.645, S 5.1, and N 40. And if we do the calculation, I come out with 1.326. But well, 1, 2, 3, 3. And so what is our confidence interval? It's x bar, which is 52.5 minus 1.33, smaller than sigma, smaller than 5 to 5 plus 1.33. Okay, and this comes out to be 51.17, smaller than mu, smaller than 53.83. We don't know where the population mean really is, but we are 90% sure it's between 51.17 and 53.83, whatever the unit. And we're done. Moving on. N equals to 15. Our little bells are starting to ring. S equals to 14.2. x bar equals to 30 and 1 minus alpha equals 0.99. Again, there's a typo in the PDF. Alright, so again, we're trying to build the confidence interval. And we need our E. And which E do we pick? Well, we don't have sigma, and we have a small sample, which means T alpha over 2 S divided by square root of N. Well, we have S, we have square root of N, we don't have T. Well, T alpha over 2 can be found on the T table, and I have two different versions of the table. I have a very similar to the one you have in your table packet, which is available to you, which has confidence level written on top, 1 or 2 tails, and I have the one that is a bit more standard, where you have nothing but just the low area alpha over 2. Either one of those works. I'm gonna show you how to deal with it using the fancier table, but we can very easily apply it to any table you want. I think the one in your table packet looks actually like this. Same idea. Oh, so first thing, if we are dealing with T alpha over 2, we need degrees of freedom, and degrees of freedom are n minus 1. So in our case, that's 15 minus 1, and that's 14. So we are looking at row 14. Right. So we're looking at row 14. So now questions, which one do we pick? Row 14. You might want, since we are looking for 99, you might be tempted to pick 99 right here. It says 99. But you have to remember how the picture looks. The picture for this looks the following. (99) being right in the middle, and on both sides being alpha over 2. And how big is alpha over 2? Well, if our 1 minus alpha was 99, then our alpha was just 1%. If our alpha is 1%, then each one of those little sections ends up being 0.5%. So we have a couple of choices. We can look at alpha over 2 as being 0.5%. We could look at the whole alpha of 1%, or we could look at this little section. This is the cumulative probability, and that in our case would be 0.99 plus 0.5%, this. Oh, sorry. Or we could look at the cumulative probability, this section, which is 99 plus half, right? So this. So we have those three choices. So let's look at back here. We have the cumulative probability, and we're looking for 99.5. So we will be looking at this column right here. We could be looking at a single section of those two, a single tail, and again, one tail. Here's your 0.5%. Or we could be looking at the whole alpha of 1%, and that's right here, two tails. of course, the table I have provided you, so this is the column we're looking at, right? Of course, the table I provided you is so nice that what you have on the very bottom, look, you have a confidence level of 99%. I even give you that. So this table is unique in the respect that it gives you all the juicy bits. There's another table that has all the things, 1 tail, 2 tail, and confidence level. So all of those, yes. This table has also one more thing that can rescue it. If we're looking at confidence level of 99%, and we're talking about Z's, we will be looking at 2575. If you look at the very bottom of this, it says here, Z-score, 2575, 99%, right? So you know we're looking at this column. There's 5 ways to figure out which column you're looking at. And now question of row. Well, row is 14. Our degrees of freedom are 14. So we're looking at this row and this column. And what we get is 2.977, which you should be able to see right here. This column, second row, 2.977. Get rid of the shake. Right. So, right here. So our E is 2. What was it? 2.977. 2.977 times what? Well, times S, which is 14.2, divided by square root of 15. And if we calculate E, it should come out to be 10.91. Double check that. 2.977 times 14.2 divided by square root of 15. 10.9149. Yep. And so what is our confidence interval? Well, that's 30 minus 10.91, smaller than mu, right? We're looking at this formula right here. Smaller than 30 plus 10.91. This comes out to be did I make a mistake? Yeah, our x is 36, not 30. 36. So that comes out to be 25.09, smaller than mu, smaller than 46.91. And again, if we look at the answer right here, it matches. Cool. Now, if you look at the rest of the problems for this, every now and then you will get a sigma. And sometimes you get a sigma, sometimes you don't. And the rest of it is good. All right, let's do the third one. And see how that one goes. So the third problem, n equals to 25, s equals to 2.7, x bar equals to 26.8, and we're talking about 1 minus alpha equals 0.9. All right, so no sigma, n and n, which means we're going to need t alpha over 2. How do we find it? Well, we have degrees of freedom, which are equal to n minus 1. So in our case, that ends up being 24. We grab our table and we find the row that we don't want. And now we're looking for confidence level of 90%, which should be right here in the middle, and we get that T alpha over 2 is 1.711. And so our E is T alpha over 2. Why? Because n is smaller equal to 30 and we have no sigma. Times S divided by square root of n. Oh, sorry, square root of n, which comes out to 1.711 times 2.7 divided by square root of 25. So E comes out to be 1.711 times 2.7 divided by square root of 25. E comes out to be 0.92394. Now I know that I have these answers already here displayed, but I still like to calculate it every now and then because it teaches me how to plug in numbers, because the last thing you want to do is end up on an exam or doing some work and getting stuck with a calculator. You need to be able to trust that your mechanical approach to the problems, which is just typing things on the calculator, actually works. And so we have our E, so our confidence interval is x bar minus E smaller than mu smaller than x bar plus E. So in our case that's 26.8 minus 0.92 smaller than mu smaller than 26.8 plus 0.92. And that should come out to 25.88 smaller than mu smaller than 27.72. Why am I picking margin of error with 2 decimal places? Because our questions has 1 decimal place here, so I'm going to give it 1 extra decimal place of precision. Do I need more? Oh, that depends on the problem. Usually the rule of thumb is 1 extra decimal place is usually more than enough. All right. So this is how we do confidence intervals for means. Let's see next set. What do we have here more? Confidence intervals for P's, sample size. All right. Here's a set of problems for sample size based on standard deviation. 3, 2, 1. Kaboom. Now, this one I made a little tricky because our confidence levels not always are the 90, 95, and 99%. As you can see here, I plugged in some extra numbers. Well, why? Because calculating sample size is a relatively simple calculation, so a little challenge added to the problem. So when we're talking about sample sizes, what we need is z alpha over 2 divided by E times the whole thing squared. But we are not always going to get sigma. Sometimes all we have is a sample standard deviation as an estimate. Again, with larger samples, which a big chunk of the samples that you're going to deal with in your real life are sample standard deviations, this is what you have to work with. So let's look at problem number 1. We have E equals to 6 S equals to 20.1 and our confidence level at 96. Oh my god, so annoying. Well, let's see. If our confidence level is 96, how big are those two extra pieces? Well, alpha in this case is 4%, which means that alpha over 2 is 2%. If we look at our Z table, we need to find 2%. If I look for 2% on my table, I'll find 2% lingering. I'll find my 2% lingering around here. Let's see if we can zoom in and take a look at. So I'm looking for 2%. I'm not looking for 0.2%, right? I'm looking for 2%. So I'm looking for 0.02. 0.02 ends up being somewhere between those two values. Which one do you pick? You pick the one that is closer. Unless you have a program to calculate it for you, which here Excel did for me. So those numbers are, but in your case, you're just gonna have to pick closer. I would avoid estimating how much in the middle it is. I would just pick a closer. This one is 18 away from 2. This one is 30 away from 2%. Right? 18, what is it? 100,000, 10,000. 100,000, 1,800,000, and this is 30 100,000s away. And then if we look at this Z table, just please here, this Z table, our 2% is going to end up being right here, between these two. It's not very visible, but this is 0.0202 and this is 0.0197. So again, this number looks better. Can I zoom in? No, sorry guys, this is as close as this camera goes. So what we have here is that the Z alpha over 2 is negative 2.05. Again, the answer I gave you has 3 decimal places. Why? Because it's computer generated, so it actually calculates the whole thing. In our case, this is the number we have. So this is the number we go with. Now again, negative Z alpha over 2 is this. So the positive version of this, Z alpha over 2, would be just 2.05. We have Z alpha 2, we have standard deviation with this. So n equals to 2.05 times 20.1 divided by 6, the whole thing squared. So 2.05 times 20.1 divided by 6 squared. and in our case n comes out to be 4716. My answer is different than this. Why? Because our critical value, our z alpha over 2, was different. But again, we cannot have a 16th of a person, so we round up. And then answer matches. Will it match always? No. If you're off by one person, I will look at your math, and if you have a slightly different answer because this is what your table was available to provide to you, that's still a correct answer. And that's done. Next one? Let's do next one. Alright. E equals to 2.2. S equals to 14.6. 1 minus alpha equals to 0.95. Well, if 1 minus alpha is 0.95, then z alpha over 2 equals to 1.96, because that's one of those three that are very common. And then again, our n equals to 1.96 times 14.6 divided by 2.2 and the whole thing squared. 1.96 times 14.6 divided by 2.2, and then we square this. And I got 169.189. Why is it different here? Again, there's a difference in how it is calculated. Our z-score might not be perfectly matching because again it comes from the table. Is this wrong? No. And then again our n comes out to be 170. Are we close enough? Yes. Alright, and then the last one for this set, E equals to 0.5, S equals to 6.1, 1 minus alpha equals to 0.8. Right, 0.8, that means that the middle part is 0.8. How big are the two sides? Well, if this is 0.8, then alpha is 0.2, which means alpha over 2 is 0.1, alpha over 2 is 0.1. Again, this plus this plus this has to equal to 100. So if we look up our table and we look up for 10%, what we're going to find is 1.28. And so again, our n equals to 1.28 times 6.1, right? Z times standard deviation divided by E, and the whole thing squared. 1.28 times 6.1 divided by 0.5 squared. And I got n equal to 243.859. .28 times 6.1 divided by 0.5 squared. Yep. That's the number I'm getting. which means that our final n, round up, is 244. What's my answer key say? 241. Why? Well, the raw score came out different. Now, why they came out different? There's a couple reasons. There could be some internal calculation on how it found critical value. It should be higher, but I don't know why it's not. Could be because I made a mistake in programming the spreadsheet to calculate things, and it gives me numbers that are off. Again, when I'm grading an exam, if you get this and I get this, I'll look at your math. If a lot of people get this versus what my answer key is, means my answer key is an issue, and I will back calculate my answer key just to make sure it isn't off. So as long as your math looks good and your error between this and what I have isn't spectacular, you're okay. Now if those errors, this becomes 400, then you probably made a huge mistake. But if it's little differences like this, there could be a difference on, hey, how did we calculate this? How did we manage to put this together? And so this is how you calculate sample size when it comes to standard deviations. All right, next. Sample size when it comes to proportions. Again, here's a set of problems. Screenshot or pause. And we're going to look at the top 3. So this is the one where we actually have to worry about what do we have available to us. So our E is Z alpha over 2 divided by E. Sorry, I've been doing it for too long. Our N, it's sample size. Angry. Our N is Z alpha over 2 divided by E squared times something, either PQ, P hat, Q hat, or worst case scenario 0.5 times 0.5. By the way, 0.5 times 0.5 is 0.25. So just this. 0.5 times 0.5 is 0.25. So we have a choice of 3 things here that go, one of those goes in here. Alright, so let's look at problem number 1. Problem number 1 says, hey, P equals to 0.713. Our E equals to 0.035. And we're looking at 1 minus alpha equal to 99%. Okay, well, N is equal to this, so this gives us Z alpha over 2F 2.575, so that should be straightforward. Now again, your confidence level might be something different. There's a couple examples we did that had something different. But for now, we are lucky, it's 2.575. Alright, so our N equals to 2.575 divided by 0.035. If you get your margin of error as a percentage, you need to convert it to a decimal place before you can plug it into here. And then comes this low. What do we have? Well, we have a P. So P is what we have. So we have the top case, and that's 0.713 times Q. How big is Q? Well, Q equals 1 minus P. So in our case, Q equals to 1 minus this. So that's 782. So 287 we do this calculation. 2.575 divided by 0.035 squared times 0.713 times 0.287, and what I got is n equal to 1107.617. Difference? Yes. Why? Because the critical value is different. Again, I'm not worried. I got close enough to the ballpark. And there's my answer. Again, why rounding up? Because we cannot ask 61% of a person to answer a survey. All right, second one. We have E equals to 0.032. We have 1 minus alpha equal to 90%, and that's it. So again, we're looking at our n. What's z alpha over 2? Well, z alpha over 2 at 90% would be 1.645. So what we have? 1.645 divided by 0.032 squared times what? Well, we don't have p, we don't have p hat, so we are looking at the worst case scenario. 0.25, right? 50%. 50 times 50% is 25%. Again, and we solve this. 1.645 divided by 0.032 squared times 0.25, and I got 660.65. So our final answer will be n equals 661. That's the smallest number of people I need to ask if I want a margin of error of 3.2% or less. Alright, and the third problem, we have p hat equal to 0.601. We have an E of 12, and we have a 1 minus alpha at 99%. This gives us z alpha over 2 of 2.575, and our n is 2.575 divided by 0.12 squared times, do we have p? No. Do we have p hat? Yes. So that's 0.601 times q. Q hat equals 1 to minus p hat, so q hat equals 1 minus this, so that's 995. And again, not 5, 3. Yes, 3. So that's 0.399. So our n comes out to E 2.575 divided by 0.12 squared times 0.601 times 0.399. So our n comes out to be 111. I'm not seeing any questions. So this is how you do sample size when you have proportions available rather than standard deviations. All right, what else can we do? Okay. Approximating binomial using normal approximation of binomial distribution. And here's a set of problems. And I'm going to take a 2-minute breather and then we can come back and do that. All right. So let's take a crack at the normal approximation of binomial distributions. If you remember, what we are looking for can be achieved using this formula. Now, again, this formula looks very big, but if you look very carefully, you really only have p hat, which could be x divided by n, but there's some p hat. There's some p. Do we need q? Well, we get q because q is 1 minus p, so we're good on that. And we need n. We need three things to calculate the z-score. So let's look at the first one. The first one, we have n equals 144. 144. So that's check. Then we have p, which is 0.618, and we're looking for probability that easy enough. We're gonna have some p hat 1 and some p hat 2. So let's calculate z-score 1. Z-score 1 is p hat minus p divided by p. We need to find q. Q equals to that. And I got z-score 1 to be negative 1.1608. But since our z-scores are on our table only go to 2 decimal places, I'm only interested in this little thing. Alright, z-score 2. It's 0.651 minus 0.618 divided by 0.618 times 0.382 divided by 144 square root across the whole thing. And that should come out to be 0.82. Now that we use z-scores, we can use our standard normal curve, and we have 0.82 over here, and we have negative 1.16 here, and we're looking for the area in between. Well, let's see, this probability negative 1.16 is 1.2. 12%, 12.3%, and then 0.82, 0.82, 79.39. This probability, all that probability is 0.7939. Again, you can see the probabilities up here. And so together this probability comes out to be 0.6709. How do I get this? 0.7939 minus 0.1230 will give me this. So this big area minus the little area. And there's my answer. 67.09 probability equals to 6%. No, still nobody talking to me. That's okay. Okay, next one. N equals to 60. P equals. Oh, apparently I got disconnected. No, I'm back connected. No. P equals to 0.533, and well, let's get Q while we add it. Q equals to 764, and then we have the probability that 0.404 smaller than p hat smaller than 0.582. Now, could I ask this in this form as well? Yeah. If you multiply all of it by n, you should be able to get this. So if you write, because x equals to p times n, or p hat times n, so we could get this number of successes. So 0.404 times 60, so we would want a 24.24 and 0.582 times 60, 34.92. Now, the number of successes cannot be a fraction, right? So what we would be looking for is that. If I ask you this question, that's the same as asking you this question. Again, if you get this kind of setup, you need to just look a little wider, because you need a whole number, because you cannot have 34.92 successes. You can have 35, and a number smaller than 35 is still matching this. Again, we're talking about where's the split between the red and the green panel. Well, it's right here in the middle. So anything right on this side is red, and anything on this side is green. But if I say green is here, on this side is still the red, right? So this is a little thing that you need to keep in mind, but small detail. All right, so we have two z-scores. Z-score 1 is p hat, so 0.4 404 minus 0.533 divided by 0.533 times 0.467 divided by 60. There's my square root. And again, that should come out to be negative 2. And then z-squared 2 equals to 0.582 minus 0.533 divided by 0.533 times 0.467 divided by 60. And this should come out to be 0.76. And because we're inquisitive, we're going to check that. Yep. 0.76076. Negative 2. 0.76. We're looking for the section in the middle. Probability from here down comes out to be 0.0228. The probability from here down all the way down becomes 0.7764, which means that the probability for the middle part should be 77 minus 2 should be about 75.36%. Cool. Moving on. Next one. N equals to 84. P equals to 0.655, which means Q equals to 0.345. And then we're looking for probability that P hat is greater than 0.733. My z-score will be 0.733 minus 0.655, right? Because it's P hat minus P divided by PQ. And that's my z-score, right? So divide by P, 0.655 times 0.345 divided by 84. So my z-score comes out to be 1.50. 1.50, and I'm looking for the area greater, so I'm looking for this part. This probability ends up being 1, right? Because the area that you get from the z-score table is to the left of the z-score, so 1.5 right here, right? It gives you this area, which means that this area is 1 minus 0.9332, which comes out to be 6.68%. and this is how you do it. Is that it? Yep, that's the couple sets of problems you get from chapter 4 and chapter 3. Cool. Alright, so I will see if I can figure out a way to publicly post that document so you have access to it. Otherwise, just pause and write down or screenshot the data. This my students in my class have access to it on their school's site, so it's under resource folder. They should be able to find it. All right. So this is this. Now next week I'm gonna start talking about chapter 5, which is hypothesis testing. In between I will run a quick introduction to chi-square, nothing big, and so that's gonna be like a short, probably like a half an hour video posted on that. And then hypothesis testing comes next week, which is chapter 5. And then after we're done with that, I'm gonna do a whole set of problems just like this, and then we're gonna hit chapter 6 running, and hopefully by then I'll finish editing the missing chapter for the textbook I wrote for you guys. All right, so I hope this covers some of your interests and whatnot, and well, enjoy statistics, I suppose, and I'll catch you guys later. Again, if you have any questions, just message me, email me, post something on the thread, and I'll take it from there. Have a great day, guys.